We're going to look at adiabatic processes and stability within the atmosphere, and how they are uniquely intertwined. In aviation meteorology, you'll often hear the shortened term Adiabatics used. This simply means the whole concept of adiabatic processes. The idea of an adiabatic process is a theoretical one that we introduce in order to understand what's happening within the atmosphere. Put simply, an adiabatic process is one which involves no transfer of energy into or out of the system that we're considering. This is a reasonable thing to do, since air is a poor conductor, and so heat energy doesn't want to flow through a section of the atmosphere very easily. There are two distinct processes: adiabatic warming and adiabatic cooling. To explain these, let's now consider a parcel of air sitting on the surface of the Earth. If we lift this parcel of air into a region of lower pressure, then it will expand. Remember, this is an adiabatic process, so no energy leaves or enters our parcel. This expansion happens because the pressure within the parcel wants to equalize itself with the surrounding pressure. The expansion process uses up some internal energy of the parcel, hence, as the parcel of air rises, it expands and the temperature actually falls. This is known as adiabatic cooling. The opposite is also true if we look at a parcel of air that is forced to drop to a lower level within the atmosphere. As the surrounding pressure increases, it forces the parcel to contract. This increases the internal temperature of the parcel. Therefore, we now have adiabatic warming. So, air moves around within the atmosphere. As it rises, it expands and cools adiabatically, and as it descends, it's compressed and so warms adiabatically. Think of a bicycle pump. As the air is compressed within the pump, it heats up, making the actual pump chamber quite warm. This is almost exactly the same process that occurs within the atmosphere. The rate at which air cools or warms, as it is forced to rise or fall, depends upon the moisture content of the parcel of air. This is called the adiabatic lapse rate. If we first consider air that is dry or unsaturated, then the maximum rate at which the temperature falls is 3 degrees Celsius per 1,000 feet of ascent, or 1 degree Celsius per 100 meters. This is called the dry adiabatic lapse rate, or DALR for short. Now let's think about the moisture content of our parcel of air, in the form of water vapor. The presence of water in the atmosphere complicates things significantly, and it's most important to understand the processes that are involved. Air can hold only a limited amount of moisture or water vapor before it reaches saturation. Warm air can hold more water vapor than cold air. This is due to the greater distance between air molecules in the warm air, creating more room for water vapor molecules. If warm, unsaturated air is cooled, it eventually reaches a point at which it becomes saturated. The water vapor will at that point start to form water droplets or condense out. This condensing out of the water vapor has one very important effect. It releases what is called latent or hidden heat. So we say that the process of condensation releases latent heat. Let's consider our parcel of warm, dry air again. If we force it to rise, the temperature will fall at the dry adiabatic lapse rate, or DALR, of 3 degrees Celsius per 1,000 feet, or 1 degree Celsius per 100 meters of lift, as we stated earlier. When the temperature falls to a certain level, condensation will take place. The water vapor, previously invisible to the naked eye, becomes visible. In other words, clouds will form. If the process of lifting and cooling continues, then more vapor condenses, releasing more latent heat. The release of latent heat has the effect of slowing down the rate of cooling. Therefore, the lapse rate in saturated air, that is, cloud, will be very different to that of unsaturated air due to the release of latent heat. This new lapse rate is called the saturated adiabatic lapse rate, or SALR, and is, on average, 1.8 degrees Celsius per 1,000 feet of lift, or 0.6 degrees Celsius per 100 meters. This is the rate at which saturated air will cool if forced to rise. The SALR is not constant through the troposphere. It reduces the higher up you go, and in fact, the saturated adiabatic lapse rate is almost exactly the same as the dry adiabatic lapse rate in the upper reaches of the troposphere. This is because the amount of water vapor that is required for saturation reduces at lower temperatures. It therefore follows that the amount of latent heat that is released also reduces as a parcel of air rises. The most commonly used average lapse rate of the SALR is 1.8 degrees Celsius per 1,000 feet, or 0.6 degrees Celsius per 100 meters. However, the actual rate varies from around 1.2 degrees per 1,000 feet at 26 degrees to 2.2 degrees when the temperature is around minus 10 degrees. Now we're going to look at the issue of stability. The stability of air depends upon two things: its temperature and moisture content, or humidity. Air is stable if it returns to its original level after being given an initial movement upwards. Thus, if a parcel of air is surrounded by air which is the same temperature as our parcel, the conditions are stable. The parcel will merely want to stay where it is. If it's given a push upwards, it will settle back to its original position. Note that the air is stable when both saturated and unsaturated conditions are considered. Air is unstable if, after an initial movement upwards, it continues to rise. In other words, it's buoyant. This happens when the parcel of air finds itself surrounded by cooler air. We now have three different lines on our diagram, and we're going to use these to explain stability. These lines are the DALR, the dry adiabatic lapse rate, the SALR, or the saturated adiabatic lapse rate, and the ELR, the environmental lapse rate, which is the actual prevailing conditions at any one point in the atmosphere, since air is rarely completely dry or completely saturated. Note, though, the ELR is not fixed. It is very variable and will be different from day to day.